So my talk is about an overview of a conceptual model of the geothermal system of the Upper Rhine Graben. So I think I will give some clues of previous question, we will see. So the Upper Rhine Graben is located in the borderland of East France and West Germany. What you know that the oil exploitation in the area of Pechelbronn highlighted an abnormal thermal gradient. Indeed, at the beginning of the 20th century, a thermal gradient of 10 degrees per 100 meters was measured at Soultz-sous-Forêt, between the surface and 400 meter depth. After the 70s energy crisis, Soultz was targeted for deep geothermal exploitation as of 1985. And following the development of the scientific pilot of Soultz, several deep wells were drilled in Landau. I don't know if you can see it, yes. And in Chime, just in south of Landau, Rettershofen also, and Vandenheim and Ilkirch in the area of Strasbourg that are still in progress. All these deep geothermal wells are in the basement and are concentrated in the central part of the Graben. This operation demonstrates the feasibility of exploiting the deep geothermal brine in the basement of the Rhine Graben. And now we are looking for a wider and optimized development of the deep geothermal brine exploitation in the Rhine Graben as lithium co-extraction and multi-site exploitation, for example. To reach that goal, we need a good understanding of the deep geothermal system. For example, how does the deep geothermal fluid circulate? Where are the main inflow areas? What are the characteristics of the main pathway? Where are the outflow areas to have a better setting of the next exploitation site? So if some of these questions have been fully or partially answered thanks to more than 35 years of research, started with Soultz-sous-Forêt pilot plants, other questions still need to be tackled. And in this presentation, I propose to guide you through a rapid investigation to draw a picture of our current understanding of the Upper Rhine Graben deep geothermal system. And we will find hints in the geological story of the Graben, in the geochemical investigation, and also in the thermal and mechanical data and models. So the Rhine Graben is a part of the European Cenozoic Reef system, but the structure leading to the current structure of the basement is far from simple. The Rhine Graben basement is composed by the roots of the Variscan mountain belt, and it has been structured since then, going through a long tectonic story of more than 300 million years. The basement of the Graben is expected to be mainly formed by metamorphic and plutonic rocks, resulting of the compressional tectonic. For these rocks are characterized by a low permeability, and the fluid flow mainly through the fault and fractures, as said by Lenny previously. As a result, the fault network has a really strong and important role in the geothermal system, as it constitutes the main fluid pathway. So I won't go really deep into the detail, but I would like to highlight that at the end of the Variscan orogeny, the basement is mainly structured by a west-southwest, east-northeast trending thrust front, a major and large northeast-southwest, sinistral strike slip fault system called European Rhine Shear Zone, probably associated with nor-northwest-south-southwest conjugate dextral strike slip faults and nor-northeast-south-southwest normal faulting. And finally, we have a major nor-northwest-south-southwest west-dipping normal fault nowadays exposed in the eastern Graben shoulder. This early structuration of the basement, has probably created the weakness direction for further reactivation and controls the early stage of rifting. After a relatively quiet Mesozoic period, during the Eocene, the paroxysm of the Alpine orogeny resulted in the reactivation of the Variscan faults. The major rifting process took place from Oligocene to early Miocene, and not there's still a debate on ongoing debate about the process leading to the rifting. So anyway, the resulting basin is split in 3 segments separated by accommodation zone. The first north-northeast trending southern segment, and then we have also a northeast central segment bordered to the west by the Saverne fault zone, and in the north, a north to north-northwest trending segment. The resulting fault network is composed by a northeast-southwest main direction conjugated to northwest-southeast fault system and by a north-south normal faults. It's also shown at the scale of the site, and you see here a density Wulfsnet of the fracture picked in the south wells. So the graben is also characterized by the east-west asymmetric structure assumed to be related to the Upper Rhine shear zone. The northern part of the graben is the deepest in its eastern bound, while the southern part of the graben is the deepest in its western bound. So, if the geology gave us some clues on the path network of the fluid, the geochemistry will give us some clues about the fluid flow direction and where it did come from. So first we have to notice that we have very similar geochemical composition of the brines discharged from the deep wells of Landau, Insheim, Sulz, Rittershofen, Cronenbourg, and Vandenheim, except for the calcium and strontium concentration value that are lower close to Strasbourg, in the Strasbourg area. The main characteristic of the brine is that we have NaCl brines with a total dissolved solid value around 100 grams per liter and a pH value close to 5. The brines result from a mixing process between brines formed by evaporation of seawater, meteoric freshwater, and contributions from halite dissolution. So all these brine of all the deep geothermal wells probably have the same origin. The thermometric relationships and the mineralogical assemblage at the equilibrium with the brine suggest that the deep brine could probably originate from Triassic sediment formation at temperature close to 225 degrees Celsius. And if we have a look on the map, on the temperature map at the top of the basement, we can see that we reach the temperature of 200 degrees at the top of the basement only on the east part of the graben. And here is a map, a temperature map at the top of the Buzenstein, and we can see that we go higher than 200 degrees only on this area, on the eastern part, close to Karlsruhe. So the deep brine is probably heated up close to the eastern bound of the graben, close to Karlsruhe, in the southwest part of Karlsruhe, before spreading westward and southwestward. That's a clue given by the geochemical data. Now, some clues from the temperature maps. First, we can note that in the central segment, we have a non-uniform gradient, geothermal gradient, laterally and with the depth. And note also that we have a quasi-linear gradient in the accommodation zone close to Strasbourg, at least until 3 kilometer depth. And we also measured in Vandenheim well up to 5 kilometer depth. Finally, in the southern part of the segment, we have a higher gradient in depth than in the shallower sedimentary layers. So let's go now more into details with the temperature maps for the central segment. So we can see that between the surface and 1 kilometer depth, we have a high gradient here in yellow, close to Sulz-Forêt and Landau. We still have this high gradient between 1 and 1.5 kilometer depth, and we had the site of Rittershofen here. Between 1.5 and 2 kilometer depth, we have an eastward transfer of the high thermal gradient, whereas the areas of Sulz and Landau show a low thermal gradient. Between 2 kilometer depth until 3 kilometer depth, we have here the map, we have a very low thermal gradient that expands to the whole area of Landau, Sulz, and Rittershofen. So we can correlate the high temperature gradient, the high thermal gradient, with conduction process, mainly so in the shallow sedimentary layer, whereas in the low gradient are correlated to convection cells in the Trias and in the top of the basement. And these convection cells are enabled thanks to the high fracturation rate.
Marianne, you have 4 minutes left.
10 minutes, okay, thank you. So I'm almost finished. So the last clue I would like to present is about the contribution of the geomechanical modeling to the system understanding. And the question we try to tackle with this kind of modeling is, where are the areas with the lowest compressional stress, as this lowest compressional stress is considered favorable for upflow. So it's a work presented in detail by Antoine Armandine-Leland in his paper in 2019. And we create a numerical model of the central part of the Upper Rhine Graben. It's the first model, it needs to be improved. And we use a discrete factor network approach. The faults are explicitly considered in the model. And we try to simulate the nowadays stress state in the faulted graben basement, taking into account the modification of the mean stress due to the fault. So I won't go into the detail of the numerical modeling, but here is just the result. We can see on this map the mean compression stress, and in the reddish color we have low compressional stress. So we can see that within the graben we have low compressional stress close to Sulz-sous-Forêt in the south part of Strasbourg. That is mainly the accommodation zone, and in the east of Speyer. This result met roughly the thermal anomalies. That is really not so bad, not really totally good, but not so bad. We need now a better integration of the main geological key structures to have a better result and to be able to have a good interpretation of that result. And then, as a sum up of this presentation and as an integration of the different clues I presented here, I would like to present a proposition of a conceptual model of the deep geothermal system of the central segment of the Upper Rhine Graben. And the main key of this system are the inflow zone that lie in the east part of the Graben, probably in the southwest of Karlsruhe. It's controlled by the steep eastern border fault. And we still have questions about the role of the East Rhine detachment that we can see on the outcrop on the eastern shoulder of the basement. Then we have a fluid heating and mixing with native fluid that occur in the deep and hot Triassic sandstone, always close to Karlsruhe. And we have several pathways to upflow areas mainly controlled by the Variscan accident faults, mainly oriented northeast, south-southwest, northeast, southwest, and northwest, southeast. That allow to lead the fluid to the upflow zone. We still have some remaining question about the real role of the Upper Rhine shear zone in the fluid pathway and circulation, and what is the real impact of the asymmetry. And we try currently, by ongoing work, try to tackle the question of the hydraulic conductivity of the fault depending of their set, of their direction, and the link with their structure, their infilling, and the stress set applied to the different fault. And about the hot fluid upflow, that is the most interesting for the fluid exploitation. Now, we know that the main hotspots are in the western part of the Graben, and it seems to be controlled mainly by the north-south gently dipping normal fault. We can correlate this upflow zone with low mean stress, and still remains the question of the accommodation zones, in particular close to Strasbourg, because as we saw about the heat transfer, we have a linear thermal gradient in the accommodation zone of Strasbourg that is quite different of the behavior we can observe in the area of Sulz, Landau, or Hittershofen, where we have deep convection cells in the basement and in the trias, and shallow conduction in the thermal blanket, mainly. So, thank you for your attention.
Thanks so much, Marianne. There are already questions. Leni, would you like to ask your question?
Start. Thanks for a nice talk. So I like that the pattern we find is actually consistent with what you show, which is always good because it's completely independent work. I was not fully understanding how you did this stress modeling in the mechanical model. How do you, are there fluids part of that, or is it?
No fluid. For this modeling, it's only a mechanical model. So we have a larger model. So you have the detail in the paper of Antoine Armandini-Land, but we have a larger model on which we apply the stress at the plate scale, and we see how the stress is reoriented and moving by the fault, by the faulted area of the Upper Rhine Graben. So you have on this map, here you can see all the black lines are the faults taking into account in the model, and we apply the stress that is horizontal measure stress is roughly north 170 degrees east. And we apply that stress, and we have a look on the mean compressional stress and the mean direction stress.
And the faults have a different friction, or how are they parameterized?
I'm not sure. I have to check, but I think all the faults have the same mechanical parameters in this model, the first Hoff model. But it will be interesting to change that depending of the fault set.
I'll take the question by Letizia. Letizia, do you want to ask it? Letizia doesn't want to. I don't know if you can see the chat, Marianne.
I cannot see the chat, so
I'll read it. Are we sure meteoric water is going down? And how do you get these light fluids to go down mechanically in your flow models?
Sorry, I didn't get it. Could you repeat?
Are you sure? Are we sure? So do we know for certain that meteoric waters go down because they have a lower density? And so how do you get these light fluids to go down in your flow, in your mechanical flow models?
Oh, we have no flow in the mechanical models, actually. So it's only mechanical models.
Okay.
Can I add something here for Letizia?
Sure.
You can get them go down because you have such a high hydrothermal gradient from the rift shoulders towards the Graben itself. So you have a hydraulic head gradient. That's why it goes down.
Yeah, so now I put my microphone. It's just when I look at the stress map, because you say it's easy to go up when you are not so much in compression, but the place where they go down is in compression. So are the fluid percolating?
The area where, yes, it's mainly through the fault. It's just a first model, and we need to enhance it to really to discuss that. But that was, yeah, in the inflow area, it will be more really in the related to the eastern fault, main fault, and not within the graben. So not in the blue here area, but more in this area close to the shoulder where we have a more less compressional stress.
Okay, thank you very much. And sorry, Suzanne, I was lazy with my microphone.
You got to speak anyway. Okay, we will have to move on to the third speaker.